Okay, let's find that volume of the solid between the paraboloid given by z equals 1 minus x squared over 4 minus y squared over 9 in this square, and that square, that's r, and it lies in the xy plane. So just to give you a little more for your tuition dollar, what would that paraboloid look like in space? Do you know how to draw that? Ooh, a hyperboloid? No. No hyperbola is involved in the cross section, so I know it can't be a hyperboloid. But I do know that, okay, it's an elliptic paraboloid. So what if I took out the negatives and wrote this down? X squared over 4, z equals x squared over 4 plus y squared over 9. Then it might be more recognizable as like the satellite dish, although it wouldn't really be a satellite dish if it were elliptical necessarily, but the kind of the satellite dish shaped paraboloid, right? But okay, what happens if you put a negative in front of it and distribute the negative? So if you take the opposite of the whole thing, it turns it upside down. And then if you add 1 to it, it raises it above. The vertex will be at a height of 1 above the xy plane lying on the z-axis. So just draw it freehand. So this would be at the point 0, 0, 1. And you know that because if you plug in 0 for x and 0 for y, you get a height of 1, z equals 1. And then down here where I cut it off, we're going to say that's z equals 0. Now here's the thing though. We're not integrating over this disk right here, which later on we will be. We're integrating over this. So that's the really important part to draw. You can get away without drawing this. I could probably play with that all day and not get it quite right. I got one more try. Give me one more try. All right. One more try. One more. No, okay, that's fine. So like this would be an x value of 1, that one. And this would be an x value of -1. This would be a y value of 1, and then -1, right? Okay. And so this, what we want to do then is we want to think of this as our r, and make this guy our ceiling. Does that make sense? Okay. So then it's a volume. So then the volume is going to be the integral, double integral, from, well, they are constant limits of integration, right? If you get a little creative here, you could use some symmetry, though. This guy is very symmetric. What would the equation of this, I want to check something real quick here. What would the equation of that curve be? Well, you can get it. So this is the curve where it would intersect the xy plane, right? Well, you can get it by plugging in 0 right here, right? Yeah. So you would get x squared, putting the 0 on the other side, or let's put the 1 on the other side and put these guys where the 0 is. So x squared over 4 plus y squared over 9 equals 1, right? Yeah. So it's an ellipse, right? And what would this ellipse look like? The center would be 0, 0. You'd go left and right. 2. So it'd actually be, let's just estimate where it'd be at. And then up and down, 3. So this again is totally unnecessary, but I just wanted you guys to have an idea, a little more, like I say, a little more for your tuition dollar. It was kind of important to make sure that this ellipse totally encompasses R. So really the way we're thinking about it, a more correct 3D picture would be to draw, I mean, this isn't correct, but it's more correct, to draw the R like that, right? And so it's like we're finding the volume with walls defined by just extending these lines upward as vertical planes, and then wherever it intersects, so it's going to intersect somewhere up here. And I'm making my picture look worse, but it's going to intersect somewhere up there. And so you'll have your walls defined by x equals 1, x equals -1, y equals 1, y equals -1 in space. And then the ceiling is still defined by this little part right here. Does everybody see that? So I kind of went off on a tangent there. Not necessary. You can trust that these problems you won't have to worry about things like that. But I wanted to make sure that my region R was totally inside what you would get if you intersected the paraboloid with the xy plane. So you don't need to worry about any of that. Limits of integration are constant, and they're both -1 to 1, right? Now, if you do want to get fancy, as I was about to say, your roof is going to be this guy. And then it doesn't matter, dy dx. If you did want to get kind of fancy, you could use symmetry here. You have to be really careful when you use symmetry. But because this square is centered at 0, 0, 0, 0, 0, if you want to talk about space, then you could just find the volume above this region and multiply by 4. But that's only because the paraboloid itself is so symmetric, and its vertex is right at an x coordinate of 0 and a y coordinate of 0 as well, right? So you do have to be very careful when using tricks like that. So if you really want to save some time, what could you do here? Well, go from 0 to 1, 0 to 1, and then multiply by 4. Does that make sense? So that's kind of a neat way to do it. And then what do we get when we integrate? Well, we got to integrate with respect to y first, right? So I don't think it's going to be pretty, but it should be doable. So 4 times the integral from 0 to 1 of y. Okay, we're going to integrate 1 with respect to y, get y, and then minus x squared over 4 times y, and then minus, that's supposed to be a y squared. So what is that going to be when you integrate it? Minus y cubed over 27, evaluated from 0 to 1, and then dx. So that will save some time. And then we're plugging in for what? We just integrated with respect to y, so we're going to plug in that 1 for y, and then when you plug in 0, everything zeroes out, doesn't it? So you just end up with 4 times the integral from 0 to 1. What is that going to be? 1 minus what? Just x squared over 4 minus 1 over 27. And then dx. So now integrate. What do you get? With respect to x. And then x cubed over 12. And then minus 1/27 x, evaluated from 0 to 1. So you get 4 times, 1 minus 1/12 minus 1/27. And, what's the common denominator between 12 and 27? I don't know. No, it's not 12 because they both contain a factor of 3, right? All right, so I'll give you more for your tuition dollar. 12 is 2 squared times 3. Would you agree with that? Okay. 27 is 3 cubed. So to create the LCD, or LCM, least common multiple, LCD, least common denominator, well, you got to have a 3 cubed in it, right? And you got to have a 2 squared. So it's 4 times 27. What's that? 108. Yeah. See, you can do things in your head if you really want to. So, I don't know. I'm getting tired. You guys have to help me now. So, what would I have to multiply the 1/12 by to get in terms of the common denominator? 9. So it becomes, 108 over 108 is 1. And then 9 over 108, minus 9 over 108 And then what do you multiply 27 by? That's the 4, right? Okay, can we do that? So it's going to be 4 and then times something over 108. And then what's 108 minus 9? That's 99. Minus another 4, 95. No common factors there, right? Oh, what about 4? That was the 27, wasn't it? 95 over 27.